Hello everyone, my name is Hyunjun Lee and I'm from Seoul National University. In this talk, I'm going to present NeuroSync, a scalable and accurate brain stimulation system using safe and efficient speculation. This work was done with my fellow students at High Performance Computer System Lab and my advisor, Professor Jang-Woo Kim. Let me start with a brief introduction of the brain-inspired computing. Brain-inspired computing mimics the mechanism of the brain to understand how the brain operates and apply them to advance various areas in computer science. The following are some example benefits of the brain-inspired computing. First, it can be applied to recognition tasks such as object detection and classification, as in conventional neural network. Aside from that, it opens a broader range of applications and benefits. For example, it can benefit from the extreme low power operation using spikes. Also, by modeling the brain, it can lead to better understanding of the brain or used to model cognitive functions. The potential efficiencies and broader computing capabilities make the brain-inspired computing a powerful, emerging computing method. First, I'll explain how the brain is modeled. A brain consists of many functional units connected together. To study its behaviors, neuroscientists simplify the brain using spiking neural networks, namely SNNs. In this form, the brain is modeled with two major components, a neuron and a synapse. A neuron is a basic functional unit of the brain, and a synapse is a directed connection between the neurons. The source neuron is called a presynaptic neuron and the destination neuron is called a postsynaptic neuron. To accurately model the brain, each component keeps time-varying states. A neuron keeps two internal states called voltage and trace, and a synapse keeps weight. As the states evolve, at some point of time, a neuron's voltage may exceed a certain threshold. And then it fires a spike. The spike affects the changes in other states. First, the spike affects how the traces of the neuron evolves. Second, it changes the weight of the synapses it passes through. The weight change is a function of both pre- and postsynaptic neurons' traces. Lastly, as the spike arrives at the postsynaptic neuron, it affects the voltage of the neuron according to the weight of the synapse. At some point, the postsynaptic neuron may also fire a spike. Likewise, the spike affects the trace update and triggers the weight change of the synapse. Note that both the pre- and postsynaptic neuron triggers weight changes. The weight change triggered by the presynaptic neuron is called pre-learning, and the change triggered by the postsynaptic neuron is called post-learning. Now, I'll explain how the existing work simulate SNNs. For SNN simulation, existing simulators adopt a time-precise simulation method. In time-precise simulation method, the simulator divides the simulation time into short, discrete time quantum called time step, and then it sequentially advances the time step. To simulate the state changes, the simulator keeps the states in local memories, and it updates the state using specialized data path. For each time step, the simulator performs two main stages of simulation. The first stage is to update the internal stage of the neurons, and the second stage is to update the weight of the synapses. To help the understanding, I'll show how the simulator updates the state of example neurons, neuron 0 and neuron 1, and an example synapse, synapse 1. In the first stage, the simulator updates the state of the neurons. First, it sequentially updates the neurons' voltages. If a neuron fires a spike, the spike is stored in the spike buffer. In this case, neuron 1 has fired the spike, and the spike is stored in the buffer. And then, according to the firing activity of the neurons, it sequentially updates the traces, like this. In the second stage, it updates the synapses. To do so, it iterates over the spike buffer. and it performs pre- and post-learning for each spike using the traces of the connected neurons. Therefore, synapse 1 is updated due to the spike using the trace 0 and trace 1. After the two stages, the simulator moves on to the next time step. The simulator repeats the procedure until the simulator reaches a predefined deadline. Overall, the simulation is a simple procedure of repeating the neuron update and synapse update. However, things get complicated as the system scales. To simulate large-scale SNN, existing simulators adopt multi-core system to exploit parallelism. To parallelize the neuron update stage, each core simulates a dedicated set of neurons and locally keep their voltages and traces in the memory. Likewise, to parallelize the synapse update stage, each core simulates the fan-in synapses of their dedicated neurons and keep their weight in memory. However, the synapse update stage requires the traces of both pre- and postsynaptic neurons. Therefore, the cores also keep and update the traces of the presynaptic neurons in the memory. For brevity, use the term local neurons to indicate the dedicated set of neurons for each core, and use the term local voltage and local trace to indicate corresponding states. On the other hand, we use the term remote neurons to indicate presynaptic neurons of the local neurons and call their traces remote traces. Aside from the neuron and synapse update, multi-core simulator requires two additional stages to ensure proper communication. The first one is the spike propagation stage. In some cases, a neuron needs to transfer spikes across different cores. Therefore, the multi-core simulator connects the cores using interconnection network. And then it performs spike propagation via core-to-core communication. The other one is the global synchronization stage. For the time-precise simulation, each core should guarantee that it received all the spikes it should have received before advancing to the next time step. Thus, the cores should handshake with each other and perform global synchronization at the end of each time step. Next, I'll explain the problems of the existing simulation method. First, time-precise simulation method suffers from excessive energy overhead to update the remote traces. The reason is that the remote traces demand large per-core memory capacity compared to other components. So let's start with an example. In the example, two presynaptic neurons are connected to two postsynaptic neurons. To simulate the network in the multi-core simulator, the neurons are split into different cores, and the stage of the postsynaptic neurons exists only in a single core. Therefore, the postsynaptic neuron consumes only small per-core memory capacity. On the other hand, the traces of the presynaptic neurons exist across different cores, as it can be connected to multiple destination neurons. Therefore, it requires large per-core memory capacity to store the remote traces. Also, the trace update is extremely energy inefficient due to the low data reuse opportunity. In the time-precise simulation method, the traces are sequentially updated in each time step. Therefore, the traces cannot be reused across different time steps, resulting in poor temporal locality. Combined with its large per-core memory capacity, the remote trace update makes the time-precise simulation extremely energy inefficient. According to our analysis, remote trace memory accesses account for a significant portion of the total energy consumption. Second, the time-precise simulator suffers from high underutilization due to the frequent synchronizations among the cores. In each time step, each core updates the neurons. When a neuron fires a spike during the update, the spike is propagated to other cores, and the spike incurs synapse update in the destination cores. While some cores perform the spike propagation and synapse update, other cores should wait and stay idle before the synchronization. Also, the cores suffer from additional idle cycles to handshake with other cores for the global synchronization. We profile the ratio of the underutilized cycles due to the synchronization at various scales. The analysis shows that the ratio of the underutilized cycle increases with scale, reaching almost 80% at 64-core scale. Next, I'll move on to the key ideas. First, we identified that the time-precise simulation suffers from excessive energy overhead due to the remote trace memory accesses. For that, we propose to update the remote traces on demand and temporarily reuse the data. Second, we identified that the frequent synchronization makes the simulator highly underutilized. Therefore, we propose to relax the synchronization with rollback and recovery support. First, I'll explain collective trace update, which enables temporal data reuse of the traces. Unlike the time-precise baseline, where all the traces are updated for each time step, collective trace update updates the traces on demand. The simulator skips trace updates in the absence of a spike. Instead, it updates the traces when a spike triggers learning. By doing so, it collectively updates the same trace over multiple time steps and thus achieves high data reuse opportunities. Next, I'll explain how we relax the synchronization using safe speculation. In the time-precise simulation, the cores suffer from underutilization to synchronize at the end of each time step. On the other hand, safe speculation synchronizes the cores only periodically, so within the synchronization period, the cores speculatively advance the time step, assuming that they do not receive spikes from other cores. Thereby, the cores avoid idle cycles waiting for other cores to finish computations and communications. Note that in some cases, the speculation may fail and a core may receive spikes from other cores during the speculation. To handle such cases, safe speculation requires a rollback and recovery support to ensure accurate simulations. Now, let's dive into the details of the safe speculation. After the periodic synchronization at T0, the simulator saves the checkpoint. Then, the core speculatively advances the time step, so in this case, core 0 advances to T5, while core 1 advances to T2. At T5, neuron 0 fires a spike, and the fan-in synapses are updated. Then, neuron 3 in core 1 fires a spike at T2. In this case, core 0 receives the belated spike, which should have arrived at T2, and the core detects the misspeculations. To handle the misspeculation, core 0 rolls back the misspeculated state to the checkpoint. After that, core 0 recovers the state to the current time step, taking the belated spike into account. However, there is a problem of the rollback and recovery procedure. During the recovery, neuron firing activity may change, so in this example, the spiking time of neuron 0 changed from T5 to T3. As a result, the core rolls back the fan-in synapses to the checkpoint and recovers again. A single neuron is connected to hundreds to thousands of fan-in synapses. Therefore, the additional rollback and recovery procedure incurs significant overhead. We observed that the speculative simulation has high misspeculation penalty due to the large rollback and recovery overhead. To that end, we propose to defer post-learning to reduce the overhead. To understand how deferred learning reduces the rollback and recovery overhead, let's repeat how the baseline simulator performs safe speculation. In the baseline, the simulator updates all the fan-in synapses when neuron 0 fires a spike. On the other hand, deferred learning does not update the fan-in synapses when the postsynaptic neuron fires a spike. When one of the presynaptic neurons fire a spike, the baseline performs pre-learning. In deferred learning, the core flushes the deferred post-learning upon receiving the spike. So in this case, Core 3 flushes the deferred post-learning. Then it performs pre-learning for the incoming spike at T4. Therefore, deferring the post-learning does not affect the simulation result. At some point during the speculation, the core may receive a belated spike, and the neuron's firing activity may change due to the belated spike. So in the example, neuron 0 fires a spike at T5 instead of T3 during the recovery. In this case, the baseline simulator rolls back and recovers all the fan-in synapses because the post-learning has updated all the fan-in synapses using the misspeculated spike. However, if the simulator defers post-learning, things are different. The core rolls back and recovers only the fan-in synapses which have flushed the deferred post-learning. So in this case, only synapse 3 undergoes rollback and recovery. Therefore, it greatly reduces the overhead. Now, let's move on to how we design our simulator, NeuroSync, using the 3 key ideas. In the baseline, the simulator has 2 problems. First, it suffers from high remote trace memory access overhead due to the lack of temporal locality. Second, it suffers from severe underutilization due to the frequent synchronizations. NeuroSync effectively tackles the problems by implementing the key ideas. First, we introduce the optimized remote trace update engine, which collectively updates the remote traces by reusing the data across multiple time steps. By using reuse buffer to hold temporally reused data, it greatly reduces the energy consumed by the remote trace update. Second, NeuroSync relaxes the synchronization using safe speculation. By adopting rollback and recovery manager, NeuroSync can synchronize only periodically without affecting the simulation accuracy. However, safe speculation incurs large rollback and recovery overhead due to the belated spikes. Accordingly, we introduced the deferred learning engine which defers the post-learning. The deferred learning engine handles the list of deferred computations and flushes them on demand. Using the deferred learning engine, we greatly reduce the rollback and recovery overhead. So our resulting architecture, NeuroSync, enables fast and energy-efficient simulation. Let's move on to the evaluation results. We evaluate the performance and energy efficiency of NeuroSync in the 64-chip system against 3 baselines: baseline, collective, and speculative. Baseline indicates the time-precise baseline equipped with the state-of-the-art neuron engine and learning engine. Collective indicates the time-precise baseline with collective trace update support. Speculative indicates the simulator equipped with collective trace update and safe speculation. We evaluated the area and power consumption of NeuroSync by conducting place and route using Samsung 28nm library. And for the workloads, we adopted large-scale biological workloads with various scales. We evaluate the effectiveness of our 3 optimization schemes. The graphs show the energy efficiency and speed-up normalized to the time-precise baseline. First, by collectively updating the remote traces across multiple time steps, collective achieves an average of 2.38 times higher energy efficiency. Second, by relaxing the synchronization and thus reducing underutilization, speculative achieves an average of 1.32 times and 1.93 times higher energy efficiency and speedup over collective baseline. Note that the additional energy efficiency comes from the reduced static power consumption with the reduced simulation time. Finally, by deferring the post-learning and thus reducing the rollback and recovery overhead, NeuroSync achieves an average of 1.2 times and 1.75 times additional energy efficiency and speedup over speculative. In total, NeuroSync achieves 3.81 times higher energy efficiency and 3.37 times higher speedup over the time-precise baseline. And I would like to conclude by summarizing the main points. First, we identify two main challenges in brain simulation: the energy inefficiency to update the remote traces, and the underutilization due to the synchronizations. Next, we propose two effective solutions to tackle the challenges: collective trace update and safe speculation. Lastly, we further optimize the speculative simulation by proposing deferred learning. Thank you for your attention. I'm more than happy to answer your questions. Thank you.